Section 5.8, Fibonacci Sequence. The Fibonacci sequence was named after Leonardo of Pisa, who was also known as Fibonacci. He was one of the most distinguished mathematicians of the Middle Ages and was also credited with introducing the Hindu-Arabic number system into Europe. So here's the Fibonacci sequence. The first two terms are 1, and then the sum of these terms gives us the third term, which is 2. The sum of the second and third term give us the fourth term, and so forth. In the middle of the 19th century, mathematicians found strong similarities between this sequence and many natural phenomena. The numbers appear in many seed arrangements of plants and petal counts of flowers, also observed on the structure of pine cones and pineapples. The golden number is shown here, and this is the value that's taken of the ratio of the n plus first term to the nth term preceding it in the Fibonacci sequence, as n gets larger and larger and larger. The symbol that we use for the golden number or the golden ratio is phi, and it's approximately equal to 1.618. So the golden ratio applies in a situation like this. The ratio of the whole, AB, to the larger part, AC, is equal to the ratio of the larger part, AC, to the smaller part, CB. The golden proportion or divine proportion is shown here, and it's equal to approximately 1.618. A line segment is divided into two segments such that the ratio of the long segment to the short segment is equal to the golden ratio. If the length of the entire segment is 8 inches, what is the length of the longer segment piece of the divided segment? So we'll consider this figure to be the line segment, and we know that that length of that line segment AB is 8 inches. And we know that the ratio of the line segment AB to the larger subportion AC is going to be the golden ratio. So we can write that like this. So AB length is 8 over AC, which is what we're trying to find, and that ratio should be approximately 1.618. If we solve for AC, we'll find AC is 4.94 inches. Now, what's the length of the shorter piece? So we know the whole length was 8 inches. If we subtract 4.94, the length of the shorter piece is 3.06. And remember, we said in the golden proportion, the length of the longer piece to the shorter piece should also be the golden proportion or the golden ratio, and it is approximately, it depends on how much rounding you do here. The golden ratio also appears in architecture in the Great Pyramid in Gizeh in Egypt, built around 2600 BC. The ratio of any side of the square base to the altitude is about 1.611. And there's a scale of proportions for the human body called the modulor. And you notice here that the ratios of the length of the head to the navel is approximately 1.618 and so forth. We can also have a golden rectangle where the length over the width, A plus B divided by A, is equal to A over B, which is equal to the golden ratio. We also see the golden rectangle in nature in the form of shells, also in architecture. Greek statues, vases, and urns, and so on also exhibited characteristics of the golden ratio. We also can see this in the work of many masters, many artists from old masters to the moderns. The Fibonacci numbers appear in music. An octave on a keyboard has 13 keys, 8 white and 5 black. Those are both Fibonacci numbers. The 5 keys are in groups of 2 and 3, which are Fibonacci numbers. In the Western scale, the most complete scale, in Western music, the most complete scale, the chromatic scale, consists of 13 notes, and these are all Fibonacci numbers. Patterns that can be expressed mathematically in terms of Fibonacci relationships have been found in Gregorian chants, works of Bach, Beethoven, Bartók, a number of other musicians. A number of studies have tried to explain why the Fibonacci sequence and related items are linked to so many real-world situations, real-life situations. It appears the Fibonacci numbers are a part of a natural harmony that is pleasing to both the eye and the ear. In the 19th century, German physicist and psychologist Fechner tried to determine which dimensions were most pleasing to the eye. He found, along with psychologist Wundt, that most people do unconsciously prefer golden dimensions when purchasing greeting cards, mirrors, and other rectangular objects. So let's determine whether a sequence is a Fibonacci type of sequence, and if it is, determine the next two terms. So here are the two sequences we're going to work with. So if it's a Fibonacci type, we take two terms, add them together to get the next term. So we have 1 plus 4 would give us 5, but we don't see that in the next term. So sequence A is not a Fibonacci type of sequence. Let's look at B. Negative 1 plus 1 is 0. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 2. It is. We want the next two terms, so 1 plus 2 would be 3. 3 plus 2 would be 5. Determine if the item described is designed in accordance with the golden ratio. A formal garden has a width of 19 meters and a length of 35.54 meters. Is this a golden rectangle? So we're going to form the ratio of the length to the width, simplify it, and we do not come out with a golden ratio.